Hello, my name is Arvind Krishnan and I'm a simulation specialist at Go Engineer. This is the second part of a series of videos on some of the advanced functionalities in Solidworks simulation. In the last video, we looked at the force control method and some of the introductory advanced options in Solidworks simulation. We applied a force of 400 newtons, which was linearly incremented, and we got some results for this cantilever beam. The displacement that we saw was 21.3 millimeters, and the displacement only in the z direction was about 21.25. Now, there would be some cases where you know the amount of displacement that needs to be applied and want to know what is the amount of load that's needed to apply that displacement. To do that, we can create another nonlinear analysis, and this time we use a displacement control. I'm going to duplicate the study. I'm going to call it displacement control. The setup of the study is going to be mostly similar, other than a couple of subtle changes. I'm going to change the amount of force applied to just 1 Newton, and as before, it's going to ramp up from 0 to 1 in the 1 second pseudo time that's applied. The only other thing that changes in the analysis itself is in the properties of the study. I'm going to go to the advanced options, and I'm going to switch from a force control method to a displacement control method. In this method, the amount of displacement at a particular point, which we're going to specify now, I'm going to pick the end of the cantilever beam, which is expected to undergo maximum displacement, and I'm going to select the z-axis because that's the direction of the displacement. Here, once I hit the edit button, I can specify the curve and how my displacement changes. So at 1 second, I want a displacement of 21.25 millimeters in the positive z direction, which is downwards in this case, and I hit OK. So the increments of the displacement in this graph is what governs the different time steps. Once again, the same time increment is what defines how the study progresses from one time step to the other. The study is now ready to run. I'm going to hit the run button. As can be seen, we are right now at time step 1 and we slowly progress. You can see intermediate results as well. The one thing that should be noted is now when it says 7%, it's at 7% of the entire 21 millimeter deformation that we suggested. It's been 1 minute and 40 seconds, and we are right now at the last iteration, 100% of the displacement, and that completes the study. As expected, the displacement is about 21.5 millimeters and the z direction displacement is about 21.35. The one main output that most people would be interested in when doing a displacement control is what was the amount of loading, and for this we get a load factor output, which is a load multiplication of the initial force that was applied. I'm going to create a time history plot, and the first node is going to default to that node, or you can create a sensor to predefine loads. We're going to select that z displacement, and the y-axis would be the load factor. So what this graph shows us is that as our displacement, which is the x-axis, goes from 0 to the entire amount of about 21.25, the load factor is at 403. Once again, 403 times the force that was initially applied is going to be the amount of load that we need to get a displacement of 21.25. Comparing these results with the force control, we see that we applied a force of 400 newtons to get a displacement of about 21.25. So the two studies are in agreement with each other. So in this video, we saw how a displacement control can be used to run a nonlinear analysis. In the next set of videos, we look at some material models that a user would have access to in a nonlinear analysis. Once again, this is Arvind Krishnan and Go Engineer. My name is Arvind Krishnan and I'm a simulation specialist at Go Engineer. In this series of videos, we're going to look at some of the advanced functionalities in Solidworks simulation, which includes the nonlinear analysis and the vibration analysis. So in this study, we just have a static analysis. It's something similar to a cantilever beam with one end fixed and a force on the other end. And this is just a static analysis where one of the assumptions that's made is that your model undergoes very small deformations. As can be seen here, the part directly goes downward, which is representative of the direction of the force. Now, there is an option inside the static analysis in the properties where a large displacement flag can be turned on. What this does is when you run the study, the force is applied with varying increments and the stiffness of your part is calculated in each of those increments. So first about 13% was applied and then 63% followed by 100% of the force. In this case, it can be seen that with calculating the deformations at multiple intervals, the displacement plot is going to be more accurate as compared to just the static analysis. One thing that cannot be controlled is we cannot view the results in each of the intermediate steps, nor can we control how big each time step is taken. Which brings us to the first capability of a nonlinear analysis, where we look at a force control method where the progression of the analysis happens with an increase in the force. The force can be controlled with respect to pseudo time, as done here, where the force is just a linear increment with time. One thing that's different in a nonlinear analysis is that all the intermediate steps that are taken to reach the final position can also be seen while post-processing. In some of the properties of the analysis, here's the inputs that determine what is the amount of the time step taken for the next iteration. The initial iteration is going to be 0.01 seconds, and of course all of these values can be changed, and then each subsequent iteration is going to be between 1e-8 and 0.1. So there's a minimum of 10 iterations that are going to take place to reach the full 100%. If for any reason the solver is not able to reach convergence at this number, we are allowed 5 adjustments and it's going to go to a lower number and try to get convergence. This is one of the benefits of using a nonlinear force control analysis. If you go to the advanced option, here is the force control that's currently selected. Once this is done, we can look at the displacement results, and these results can be viewed at in different time intervals. So we can look at the maximum result, which in our case is after 13 is the 13th iteration. These results are pretty close to the results of the static analysis with the large displacement flag turned on. But this might be slightly more accurate because we were able to have smaller time steps. Also, we can view our results at the different time intervals. So at about 55% of the load, this was how the deformation looked. In the next video, we're going to see how a displacement control works. Once again, this is Arvind Krishnan at Go Engineer.